You know, there's a pervasive assumption in discussions about extraterrestrial intelligence and the search for alien civilizations, the idea that if intelligent life arises elsewhere in the universe, it will naturally progress to advanced technological civilization capable of interstellar communication or travel or megascale engineering projects, that the path from simple intelligence to advanced civilization is relatively straightforward and probable once intelligence emerges, that we should expect the universe to contain numerous advanced alien civilizations at various stages of technological development, ranging from our level to potentially millions or billions of years beyond us, with correspondingly incomprehensible capabilities. This assumption underlies the Fermi paradox, which asks where all these advanced civilizations are, if they should exist in large numbers. And it motivates SETI searches looking for radio signals or other techno-signatures from civilizations that have achieved at least our level of radio technology or beyond. The narrative is supported by extrapolating from Earth's history, where intelligence emerged through natural selection and quickly, within just a few thousand years, developed from stone tools to space flight and nuclear weapons and global communications networks, suggesting that once intelligence reaches certain threshold of capability, technological progress becomes rapid and perhaps inevitable, leading to advanced civilization within cosmologically brief time frames. The vast number of potentially habitable planets in the galaxy, estimated at billions, combined with the billions of years available for evolution, suggests that even if intelligent life is rare in absolute terms, there should be thousands or millions of intelligent species at various developmental stages, and some fraction of these should have progressed to advanced technological civilization, detectable or visible across interstellar distances through their engineering activities or communications. And I'm going to tell you why this entire assumption is fundamentally wrong, and why advanced alien civilizations almost certainly don't exist anywhere in the observable universe, not because intelligent life never evolves, but because the progression from basic intelligence to advanced technological civilization faces so many insurmountable barriers and filters that virtually all intelligent species go extinct before achieving advanced status. Why the handful of species that do develop intelligence and rudimentary technology face existential threats that become more severe as technology advances, creating a deadly convergence where more advanced capabilities generate proportionally greater risks of self-destruction, and why the timescales and prerequisites for achieving truly advanced civilization are so demanding that the probability of any species navigating all the barriers successfully approaches zero. They all went extinct not through any single catastrophic failure, but through the accumulation of barriers that each have moderate probability of causing extinction, and that compound over the millions of years required to progress from intelligence to advanced civilization. What I mean by advanced aliens requires definition, because intelligence and technological advancement exist on spectra rather than as binary categories. I'm referring specifically to civilizations that have progressed substantially beyond our current level in ways that would make them detectable or visible at interstellar distances. This includes civilizations capable of interstellar travel or communication, allowing colonization of multiple star systems, or at least sustained signaling across light years, megascale engineering like Dyson spheres or stellar manipulation producing observable signatures, control over planetary or stellar evolution allowing deliberate manipulation of environments, understanding and application of physical laws, allowing technologies we would consider almost magical persistence over millions to billions of years, allowing accumulation of knowledge and capabilities. These capabilities would represent advancement beyond our current state by orders of magnitude. In contrast, intelligence and basic technology, meaning tool use, and simple technology like agriculture and metallurgy and writing are probably much more common cosmically, but don't constitute advanced civilization in the sense that would make aliens detectable or enable cosmic scale influence. a civilization at our current level or even somewhat beyond having nuclear power and spaceflight and computers is also not yet advanced by the standards I'm discussing, because such civilization remains confined to its home planet and produces no signatures detectable beyond a few light years and persists for uncertain duration, possibly only thousands of years before self-destructing or stagnating. The core argument is that numerous filters and barriers prevent progression from intelligence to truly advanced civilization. These barriers include self-destruction through technological weapons or environmental destruction, resource depletion and diminishing returns on technological progress, evolutionary and cognitive limitations preventing indefinite advancement, cosmic catastrophes like supernovae or asteroid, impacts destroying civilizations before they mature, fundamental physical limits on energy and information, making certain technologies impossible, social and political instabilities, tearing civilizations apart, loss of motivation or drive as civilizations achieve their goals or recognize impossibility of further advancement, and the sheer timescales required for advancement during which any of these threats can strike. Each barrier has some probability of causing extinction, perhaps 10 to 90% depending on the specific barrier and circumstances. The probabilities compound multiplicatively so that navigating all barriers requires the product of survival probabilities for each, even if each individual barrier has relatively high survival probability, like 50 to 90%. The product of many such probabilities becomes very small. A civilization facing 10 barriers, each with 80% survival probability, has overall survival probability of only 0.8. 10 is approximately equal to 0.11, or about 11%. With 20 barriers, survival drops to about 1%. The more barriers that exist, and the more severe they are individually, the less likely that any civilization survives to become advanced. Let me start by examining the self-destruction barrier, which is perhaps the most obvious and immediate threat facing technological civilizations, because technology creates capabilities to destroy civilization through weapons or environmental damage that increase in severity as technology advances. Nuclear weapons developed within decades of the discovery of nuclear fission in the 1,930 seconds represent existential threat to civilization through potential nuclear war, causing immediate deaths from blast and radiation, followed by nuclear winter from smoke and ash blocking sunlight, reducing global temperatures, and destroying agriculture, leading to mass starvation. A full-scale nuclear exchange between major powers would kill billions through direct effects and subsequent famine and societal collapse, even if not causing complete human extinction. The fact that humans developed nuclear weapons so quickly after discovering atomic physics suggests this is relatively easy technological achievement that most civilizations with similar scientific knowledge would discover. The basic physics of nuclear chain reactions is fundamental, not requiring exotic insights. Once a civilization understands atomic structure and neutron physics, the path to nuclear weapons is relatively straightforward given sufficient engineering capability. This means most technological civilizations will acquire civilization-destroying weapons relatively early in their technological development, creating an extended period of vulnerability during which accident or conflict could cause self-destruction. The probability of nuclear war during any given year might be small, perhaps 0.1 to 1%, but over decades to centuries, these probabilities accumulate during the Cold War. From 1,945 to 1,991, spanning about 46 years. Humanity came close to nuclear war multiple times, including Cuban Missile Crisis and various false alarms where detection systems incorrectly indicated nuclear attack was underway. Only luck and individual judgment prevented launches that might have escalated to full exchange. If annual probability of nuclear war was 0.5%, the probability of avoiding it for 46 years is about 0.995. 46 is approximately equal to 0.79 or 79%, suggesting roughly 20% probability that nuclear war occurred during this period. Humanity survived the Cold War, but nuclear weapons persist and proliferate to additional nations, increasing the number of potential trigger points for war. Furthermore, the geopolitical competition and tensions that motivated Cold War nuclear buildups remain features of international politics, suggesting continued risk. Over the next 1,000 years, if nuclear weapons continue to exist, the cumulative probability of catastrophic nuclear war might be quite high, perhaps 50 to 90%, unless fundamental changes in human political organization eliminate war entirely, which seems unlikely given the evolutionary roots of conflict in human nature. But nuclear weapons are just one self-destruction pathway. Biotechnology and engineered pathogens represent potentially even more dangerous threat because creating novel pathogens becomes easier as biotechnology advances, while defenses against novel pathogens lag. Natural evolution occasionally produces highly lethal pandemics like the 1918 influenza, which killed 50 to 100 million people, or about 3 to 5% of global population. But natural evolution is constrained by the fact that pathogens that kill hosts too quickly don't transmit effectively. Engineered pathogens could potentially combine high lethality with effective transmission if designed deliberately to cause maximum harm. The technology to create engineered pathogens is advancing rapidly with CRISPR gene editing and synthetic biology, making it progressively easier to modify or create microorganisms with desired characteristics. Currently, such work requires sophisticated laboratories and expert knowledge, but the trend is toward democratization where smaller groups or eventually individuals could create dangerous pathogens. This creates the bioterror threat, where malicious actors intentionally release engineered pathogens to cause mass casualties, or the accident scenario where research into dangerous pathogens leads to accidental release from laboratory. The COVID-19 pandemic, which as of 2024 has killed over 7 million people officially, and likely over 15 to 20 million when accounting for excess mortality, demonstrates that even relatively mild pandemic by historical standards causes enormous disruption to global civilization. A pathogen engineered for high lethality with long asymptomatic transmission period and resistance to medical countermeasures could potentially kill a substantial fraction of global population before being contained or eliminated. Recovery from such catastrophe would be extraordinarily difficult, especially if critical infrastructure and expertise were lost. Civilization might collapse to pre-industrial level from which recovery is uncertain. As biotechnology continues advancing, the capabilities to create dangerous pathogens increase, while the number of actors with such capabilities also increases, creating growing risk. Over centuries to millennia, the cumulative probability that some actor, whether state or terrorist group or accident, creates and releases civilization-ending pathogen might be quite high, perhaps 30 to 70%. Each year that passes with biotechnology capabilities increasing and with geopolitical tensions and with potential for accidents adds to cumulative risk. Artificial intelligence represents another potential self-destruction pathway. If advanced AI systems are developed with goals misaligned with human survival and flourishing, the concern is that AI systems significantly more intelligent than humans could pursue instrumental goals like acquiring resources and preventing their shutdown that conflict with human welfare. If such systems are given substantial autonomy and power, they could potentially cause human extinction, either deliberately as means to their goals or accidentally through pursuing goals that happen to require eliminating humanity as side effect. The probability and timescale of AI existential risk are highly uncertain because we don't know whether advanced general AI is achievable or when it might be developed or whether alignment problems can be solved. But the possibility exists that within the next decades to centuries, humans or other intelligent species develop AI systems that then destroy their creators. If this probability is even 10 to 20%, it contributes significantly to the total extinction, risk-facing civilizations during their technological adolescence. Environmental destruction through climate change or pollution or ecosystem collapse represents a slower but potentially equally devastating self-destruction pathway. Human industrial civilization has already caused global average temperature increase of over 1 degree Celsius since pre-industrial times, with projections of 2 to 4 degrees Celsius or more warming by 2100 depending on emissions trajectories. The effects include sea level rise, flooding, coastal cities, more frequent extreme weather events, disruption of agriculture through changing precipitation patterns, ecological disruptions, including species extinctions and ecosystem shifts, and potential triggering of tipping points like permafrost, methane release, or ice sheet collapse that could accelerate warming. While climate change is unlikely to cause human extinction directly, it could destroy industrial civilization through crop failures and resource wars and mass migrations and economic collapse. A civilization that cannot maintain industrial technology reverts to pre-industrial state from which re-industrialization might be impossible if easily accessible fossil fuels have already been exhausted. Earth's easily accessible coal and oil deposits required hundreds of millions of years to form and are being depleted within a few centuries. A second industrial revolution attempting to restart after collapse would lack these resources, making it unclear whether technological civilization could be rebuilt. Beyond climate change, other environmental damages like ocean acidification, plastic pollution, nitrogen cycle disruption, phosphorus depletion, and biodiversity loss create multiple stresses on Earth's ecosystems. The cumulative effect of these stresses could trigger ecosystem collapses that undermine the natural systems on which civilization depends, including pollination of crops, oceanic food chains, soil fertility, and water cycling. Civilizations are embedded in biospheres and depend on functioning ecosystems. Destroying those ecosystems while pursuing short-term technological and economic growth represents a form of self-destruction through environmental degradation. So examining self-destruction pathways reveals multiple independent threats, each with significant probability of causing civilizational collapse or extinction over timescales of centuries to millennia: nuclear war, engineered pandemics, AI misalignment, environmental destruction, and potentially other threats I haven't discussed, like nanotechnology accidents or physics experiments gone wrong. These threats have cumulative probability that compounds over time. If each threat has 10 to 30% probability of causing extinction over the next 1,000 years, the probability of avoiding all of them might be only 20 to 50%. This is the first major filter preventing most intelligent species from becoming advanced civilizations. Now let me examine resource depletion and diminishing returns, which create barriers to continued technological advancement, even if civilizations avoid self-destruction, because technological progress requires energy and material resources, and as easily accessible resources are depleted, continued progress becomes more difficult, eventually hitting fundamental limits. Early technological development accesses low-hanging fruit, where easily extractable resources provide large returns on effort. Wood and coal and surface oil deposits powered the early Industrial Revolution. These resources were concentrated and accessible, requiring relatively simple technology to exploit. The energy return on energy invested, ERO, was very high, meaning that extracting and using these resources provided much more energy than was consumed in the extraction process. As easily accessible resources are depleted, extraction requires progressively more energy and technological sophistication to access deeper or lower grade deposits. Coal mining has progressed from surface deposits to deep underground mines, requiring extensive infrastructure and energy input. oil extraction has moved from gushing surface wells to deep offshore drilling and tar sands and shale oil requiring hydraulic fracturing. The EROEI has declined from 100 to 1 for early oil wells, meaning 100 units of energy extracted per unit invested, to perhaps 10 to 1 or less for modern unconventional sources. Eventually, EROEI approaches 1 to 1, where it takes as much energy to extract resources as the resources provide, making further extraction pointless. Mineral resources follow similar depletion curves. High-grade ore deposits are mined first, leaving progressively lower-grade ores requiring more energy to extract and refine. Copper ore grades have declined from 3 to 5% copper content to less than 0.5% today, requiring processing much larger volumes of rock to obtain the same amount of metal. Rare earth elements essential for many modern technologies exist in very low concentrations, requiring extensive processing with environmental impacts. As grades decline, the energy and environmental costs of extraction increase, potentially making some technologies unsustainable. The depletion of easily accessible resources creates trap for civilizations attempting to reindustrialize after collapse. A civilization starting from pre-industrial state needs energy sources and metals to build industrial infrastructure. But if the easily accessible coal and oil have been exhausted by the first industrial civilization, the second attempt has no readily available energy sources. Gathering wood for fuel is insufficient to support industrial-scale metallurgy. The civilization might be permanently stuck at pre-industrial level, unable to restart technological progress. This suggests that each planet might get only one chance at technological civilization, and if that civilization collapses before achieving sustainability or space resource access, there may be no second chance. Even without catastrophic collapse, resource constraints could limit how far technology can advance. Many proposed advanced technologies require enormous energy and material inputs that might be unsustainable. Space colonization requires launching massive payloads into orbit, requiring enormous energy. Dyson sphere construction would require dismantling planets to obtain construction materials far exceeding anything achievable with planetary resources. Interstellar travel requires energies comparable to stellar outputs. These technologies might be physically possible, but practically impossible because civilizations lack sufficient resources to implement them. The concept of diminishing returns applies to technological progress itself. Early scientific discoveries provide large, immediate practical benefits. Understanding electricity enables electric motors and lighting and communications, transforming civilization. Understanding atomic structure enables nuclear power and modern chemistry. But as the low-hanging fruit of science is picked, subsequent discoveries become more difficult and provide smaller practical benefits. Particle physics discoveries of the past decades have revealed interesting facts about fundamental particles but haven't produced practical technologies comparable to earlier discoveries. The cost of fundamental physics research has increased exponentially, while practical returns have plateaued. Some have argued that scientific progress follows S-curve, where initial rapid progress eventually saturates as the field matures, the rate of transformative discoveries declines, and research shifts to incremental refinements. If science as a whole follows this pattern, then technological progress derived from science would also saturate. Civilizations might reach a point where continued research produces diminishing returns insufficient to justify the costs. Technological stagnation sets in not because all possible technologies have been discovered, but because discovering and implementing remaining technologies becomes prohibitively difficult and expensive. The thermodynamic limits of computation and information processing also create fundamental barriers. Landauer's principle states that erasing information requires dissipating at least kT line 2 of energy, where K is Boltzmann's constant and T is temperature. This sets minimum energy cost for computation. Improving computational efficiency can approach but never violate this limit. Similarly, there are limits on information storage density related to atomic or quantum mechanical scales. A civilization might develop computers approaching theoretical efficiency limits, but cannot go beyond those limits no matter how advanced they become. This puts ceiling on computational capabilities. Energy extraction from stars is limited by the star's luminosity. A Dyson sphere capturing all of the sun's output would provide about 4 times 10, 26 watts, which, while enormous, is still finite. Advanced civilizations attempting to operate at scales beyond this would need multiple stars, but coordinating activities across interstellar distances faces light-speed communication delays. A civilization spanning 100 light years has 100-year round-trip communication time, making centralized control impossible. The civilization fragments into independent regions that evolve separately, potentially losing technological coherence. So examining resource depletion and diminishing returns reveals that technological progress faces natural limits from resource availability, energy costs of extraction, thermodynamic limits on information processing, and coordination problems across interstellar distances. These limits might prevent civilizations from reaching the kind of advanced status often imagined in science fiction. Civilizations might plateau at some intermediate level, unable to progress further due to resource constraints and diminishing returns on research investment. They might persist at this plateau for extended periods, or they might decline as resources are exhausted. Either way, they don't become the super advanced civilizations often imagined. Now let me examine evolutionary and cognitive limitations that might prevent species from achieving or maintaining advanced civilization, because intelligence and technological capability are products of biological evolution, which is constrained and creates organisms optimized for ancestral environments rather than for civilization building. Human intelligence evolved in small group hunter-gatherer environments where skills like social cooperation, pattern recognition, communication, and tool use provided survival and reproductive advantages. Our cognitive abilities are impressive, but are optimized for solving problems faced by our ancestors, like finding food and avoiding predators, and cooperating in groups of 50 to 150 individuals, not for the abstract reasoning and long-term planning and cooperation at massive scales required for advanced technological civilization. Many cognitive biases that served us well ancestrally create problems for civilization. Present bias causes us to discount future consequences, leading to short-term decision-making that sacrifices long-term sustainability. In-group bias creates tribal thinking and conflict between groups, hampering cooperation at civilizational scales. Confirmation bias makes us resistant to evidence contradicting our beliefs, preventing rational updating when needed. Optimism bias causes systematic underestimation of risks, leading to inadequate preparation for threats. These biases are hardwired into human cognition by evolution and are difficult to overcome through education or cultural institutions. The mismatch between ancestral environments and civilizational environments creates psychological problems, including anxiety, depression, obesity, addiction, and social alienation that plague modern populations. Humans are evolved for small group face-to-face interaction, not for anonymous urban life. We're evolved for physical activity, not for sedentary office work. We're evolved for natural environments, not for concrete cities. The result is widespread psychological distress that reduces quality of life and potentially threatens civilizational stability if significant fractions of population are dysfunctional. Furthermore, human cooperation is maintained partly through reciprocity and reputation, which work well in small groups, where repeated interactions occur and reputation can be tracked. But at civilizational scales, with millions to billions of individuals and largely anonymous interactions, these mechanisms break down. Maintaining cooperation requires formal institutions like laws and police and courts, but these institutions are costly and imperfect. Cheating and corruption remain endemic in large societies, creating inefficiencies and potentially threatening social cohesion. The larger the civilization grows, the more difficult cooperation becomes. Human intelligence itself might have fundamental limits related to brain architecture and energy costs. The human brain represents about 2% of body mass, but consumes about 20% of metabolic energy. This is near the upper limit of what can be supported given constraints on energy acquisition and distribution. Substantially increasing brain size or computational capacity would require proportionally more energy, which might not be sustainable. Furthermore, larger brains require longer development periods and create obstetric challenges. Humans already have long childhood, requiring extensive parental investment and difficult childbirth due to large infant head size. The possibility of enhancing human intelligence through genetic engineering or neural implants or other interventions is often suggested as solution to cognitive limitations, but these technologies face severe practical and ethical problems. Genetic engineering of intelligence faces the problem that intelligence is polygenic, depending on thousands of genes whose interactions are poorly understood. Editing multiple genes to enhance intelligence could have unintended consequences, including harmful side effects. Furthermore, enhanced intelligence might require larger brains with associated energy and obstetric costs. Neural implants face challenges of brain-computer interfaces where getting electrodes into the brain and extracting useful signals and providing useful inputs without damaging tissue is extraordinarily difficult. Even if cognitive enhancement were achievable, evolutionary dynamics might prevent its widespread adoption. Enhanced individuals might have reproductive disadvantages if enhancement is costly or if it makes individuals less socially compatible with unenhanced populations. If enhanced individuals don't reproduce faster than unenhanced ones, then enhancement doesn't spread through the population. Furthermore, enhancement creates potential for inequality, where enhanced elites dominate unenhanced masses, creating social instability. The challenges of cognitive enhancement suggest it might not be a practical solution to human cognitive limitations. Alien intelligences would face analogous limitations from their own evolutionary histories. Any intelligence arising through natural selection will be optimized for ancestral environments, not for civilization building. Alien cognitive biases might differ from ours, but would still exist as products of their evolutionary pressures. Aliens would similarly face challenges of cooperation at large scales and mismatches between evolved psychology and civilizational requirements. The idea that alien intelligence might be fundamentally superior to human intelligence has no basis. Intelligence is expensive, and evolution optimizes for sufficient intelligence to survive and reproduce, not for maximum intelligence. The social and political instabilities that arise from cognitive and evolutionary mismatches pose additional threats to civilizational longevity. Human history is replete with civilizations that collapse due to internal conflicts, political dysfunction, economic breakdown, or social fragmentation, despite possessing considerable technological sophistication. The Roman Empire, Mesopotamian civilizations, Maya civilization, and countless others achieved impressive technological and organizational capabilities, but eventually collapsed. While the proximate causes varied, including environmental degradation and external invasions and disease, underlying factors often involved the inability to maintain political cohesion and effective governance over extended timescales and large territories. Modern global civilization faces similar challenges at unprecedented scale, with over 8 billion humans organized into nearly 200 nation-states with competing interests and different political systems and cultural values. Maintaining international cooperation on global challenges like climate change or nuclear weapons control or pandemic prevention has proven extraordinarily difficult. Short-term national interests regularly trump long-term collective welfare, and the possibility of major conflicts, including great power wars, remains significant despite the existential risks such wars would pose in the nuclear age. The timescales for political planning and action are mismatched to the timescales of many civilizational threats. Democratic political systems operate on election cycles of 2 to 6 years, creating incentives for politicians to prioritize short-term visible benefits over long-term risks. Even authoritarian systems with longer-term planning, horizons of decades, struggle to maintain consistent policy over generations as leadership changes. Addressing threats like climate change or asteroid impact risk or gradual resource depletion requires sustained coordinated action over decades to centuries, which is beyond the demonstrated capability of human political institutions. Economic systems based on growth and competition create pressures toward exploitation of resources and environmental degradation, even when the long-term consequences are understood. Individual actors maximizing short-term profit create collective harm through tragedy of the commons dynamics. Regulating such behavior requires effective governance, which, as discussed, is difficult at global scale. Furthermore, economic inequality both within and between nations creates political tensions that can escalate to conflict. The richest individuals and nations consume disproportionate resources while billions remain in poverty, creating resentment and instability. Cultural and religious differences provide additional sources of conflict. Humans organize into ideological groups with different worldviews and values and goals. When these groups perceive their interests as incompatible, conflict arises. While modern secular democracies attempt to manage such conflicts through tolerance and pluralism and compromise, the success is uneven, and many regions remain mired in religious or ethnic conflicts. Furthermore, the rise of nationalism and populism in many countries suggests renewed emphasis on group identity and rejection of cosmopolitan values, potentially making global cooperation harder. The possibility of civilizational stagnation, where progress halts due to loss of motivation or sense of purpose, represents another potential outcome. If a civilization achieves comfortable existence where basic needs are met and no compelling challenges remain, subsequent generations might lose the drive that motivated earlier technological development. Some historical civilizations, like ancient Egypt, maintained stable cultures for millennia with minimal technological change after achieving satisfactory adaptations to their environments. A technological civilization might similarly reach a plateau where further advancement seems unnecessary or too difficult and simply maintain existing capabilities indefinitely. But stagnation creates vulnerabilities because maintenance of complex technological systems requires sustained effort and expertise. If knowledge is lost through lack of practice or if maintenance systems degrade, technological capabilities can decline. Roman concrete and engineering techniques were lost during the medieval period and had to be rediscovered centuries later. A stagnating civilization risks gradual decay of its technological base through entropy and knowledge loss. Furthermore, stagnation leaves the civilization vulnerable to new threats it hasn't prepared for, including cosmic catastrophes or internal problems that gradually worsen. Some researchers have proposed that advanced civilizations might deliberately limit their technology and adopt sustainable steady-state economies rather than pursuing unlimited growth. This would avoid resource depletion and environmental destruction at the cost of not achieving maximum possible technological advancement. Such civilizations might persist for extended periods at intermediate technological levels, but would not become the galaxy-spanning super-advanced civilizations often imagined. They would remain confined to their home systems and would not be detectable at interstellar distances, making them effectively invisible despite existing. So examining evolutionary and cognitive limitations and social and political instabilities reveals fundamental barriers to achieving and maintaining advanced civilization. Intelligence is constrained by evolutionary history and brain architecture. Cooperation at civilizational scales is difficult and requires institutions that are imperfect and costly. Political systems are inadequate for long-term planning and coordination. Economic pressures drive unsustainable resource exploitation. Cultural differences create conflict, and civilizations might stagnate or decline even if they avoid catastrophic failures. These factors make the progression from basic intelligence to advanced civilization difficult and uncertain, with many opportunities for failure. Now, let me examine cosmic catastrophes that can destroy civilizations regardless of their technological sophistication, because even civilizations that navigate the self-destruction barriers and resource constraints and social challenges remain vulnerable to external threats from their cosmic environment. As I discussed in previous contexts, supernovae and gamma-ray bursts represent existential threats to civilizations within tens to thousands of light years. The frequency of these events is such that most regions of galaxies experience sterilization on timescales of tens of millions of years. Civilizations attempting to persist over the millions of years required to progress from basic to advanced technology face substantial probability of being destroyed by nearby supernova before achieving advanced status. But supernovae are not the only cosmic threat. Asteroid and comet impacts represent more frequent, if less severe, hazards. Earth has experienced numerous major impacts throughout its history, including the Chicxulub impact 66 million years ago that contributed to the extinction of the dinosaurs. Impacts of this scale occur roughly every 100 million years on average, with smaller but still devastating impacts occurring more frequently. A 1-kilometer asteroid impact would have regional to global effects depending on location. A 10-kilometer impact, like Chicxulub, would cause global winter and mass extinctions, potentially destroying technological civilization, even if not causing human extinction. The frequency of civilization-destroying impacts can be estimated from the distribution of near-Earth objects, objects larger than 1 kilometer that cross Earth's orbit number in the thousands. The average interval between impacts by such objects is roughly 500,000 years. Objects larger than 10 kilometers are rarer, with impact intervals of tens of millions of years, but these statistics are for Earth specifically. Other planets and other star systems would have their own populations of impact threats with frequencies depending on local conditions, including the architecture of their planetary systems and the density of comets and asteroids. Civilizations could potentially detect and deflect asteroids with sufficient warning time using rockets or gravity tractors or kinetic impactors or other techniques, but this requires sustained monitoring and response capabilities over millions of years. A civilization that lets its asteroid defense capabilities lapse for even brief periods faces renewed risk. Furthermore, deflection requires detecting objects years to decades in advance, which is challenging for objects on first-time passage through the inner system. Comets from the Oort cloud can arrive with little warning, making deflection difficult. The cumulative probability of catastrophic impact over millions of years remains significant, even with defense efforts. Solar flares and coronal mass ejections represent another threat to technological civilization, particularly to electrical infrastructure. The Carrington event of 1859 was a massive solar storm that, if it occurred today, would likely cause trillions of dollars of damage to power grids and satellites and communication systems. Recovery could take months to years, during which modern civilization would be severely disrupted. Larger events that occur perhaps once per 1,000 years could be even more devastating, potentially destroying substantial fraction of technological infrastructure simultaneously. Civilizations dependent on complex electrical systems are vulnerable to such disruptions. Rogue planets or stellar encounters that disrupt planetary orbits represent extremely rare but catastrophic threats. Gravitational perturbations from passing stars can alter orbits of planets, potentially ejecting them from their star systems or causing collisions. The timescales for such events are extremely long, with stellar encounters occurring perhaps once per billion years for typical stars in the galaxy. But over the hundreds of millions to billions of years a civilization might exist, the cumulative probability becomes non-negligible. Furthermore, rogue planets wandering through space could potentially impact or perturb planetary systems, though detection might provide some warning. Changes in stellar output as stars evolve, represent long-term threats that all civilizations face. Main sequence stars like the Sun gradually increase in luminosity over billions of years. The Sun has increased luminosity by about 30% since formation and will increase another 10% over the next billion years. This gradual brightening will eventually make Earth too hot for liquid water and life, perhaps in 500 million to 1 billion years. Civilizations on planets around similar stars face analogous timescales. While billions of years seems like ample time, it's comparable to the time required for complex life to evolve, meaning civilizations might not have time to develop advanced space capabilities before their home planets become uninhabitable. More massive stars evolve faster, with main sequence lifetimes of only millions to tens of millions of years before expanding into red giants. Civilizations arising on planets around such stars would have very limited time to develop advanced technology before their star's evolution destroys their planet. This restricts the set of stars that can host long-lived civilizations to relatively low-mass stars with lifetimes of billions of years, but such stars are minority of all stars, reducing the total number of potential sites for advanced civilizations. Galactic dynamics, including passages through spiral arms and gravitational perturbations from nearby stars, create periodic environmental variations that might affect planetary habitability. Earth's orbit around the galactic center takes about 225 million years, during which the solar system passes through spiral arms roughly every 100 to 150 million years. Spiral arms have higher stellar densities and more supernovae and cosmic ray flux. Some researchers speculate this might correlate with mass extinctions, though evidence is weak. Regardless, the varying galactic environment means that habitability conditions change over tens of millions of years, potentially creating challenges for civilizations attempting long-term persistence. The eventual heat death of the universe represents ultimate cosmic catastrophe that no civilization can escape, but this occurs on timescales of trillions of years, far longer than relevant for discussing current absence of advanced civilizations. More immediate cosmological effects include the accelerating expansion of the universe driven by dark energy, which causes galaxies beyond the local group to recede beyond our cosmic horizon, making them forever unreachable. This doesn't threaten civilizations currently, but limits the ultimate extent of any civilization's influence to its local galactic cluster. So examining cosmic catastrophes reveals that civilizations face numerous external threats throughout their existence, including supernovae, gamma ray bursts, asteroid impacts, solar storms, stellar evolution, and other hazards. Each threat has some probability of causing extinction or civilizational collapse. Over millions of years, the cumulative probability that at least one such catastrophe destroys a civilization becomes substantial, perhaps 30 to 70%, depending on location and circumstances. These external threats combine with internal threats from self-destruction and resource constraints to create multiple independent pathways to extinction, reducing the probability that civilizations survive long enough to become advanced. Now let me examine the fundamental physical limits that constrain what even advanced civilizations can achieve, because understanding these limits shows that many capabilities imagined for super advanced aliens are likely impossible, making the concept of arbitrarily advanced civilization questionable. The speed of light limit from special relativity constrains how fast information and objects can travel through space. No physical object with mass can reach or exceed light speed. And even approaching light speed requires enormous energy, as the Lorentz factor gamma equals 1 square root 1v squared divided by c squared approaches infinity as velocity v approaches c. For v equals 0, 9c, we have gamma is approximately equal to 2.3, meaning kinetic energy is 1.3 times rest mass energy for v equals 0. 99c, we have gamma is approximately equal to 7, meaning kinetic energy is 6 times rest mass energy. The energy requirements for interstellar travel at relativistic speeds are prohibitive, as I've discussed in previous contexts. Accelerating even modest payloads to speeds sufficient for crossing galactic distances in reasonable times requires energies comparable to stellar outputs. This creates practical barrier to large-scale interstellar expansion, even if not a fundamental impossibility. Furthermore, the light speed limit means that civilizations cannot maintain coherent unity across interstellar distances because communication delays of years to thousands of years prevent real-time coordination. Galactic civilizations would fragment into independent regions. Faster-than-light travel is often proposed as a solution, allowing advanced civilizations to bypass light speed constraints. But no known physics allows FTL travel. Special relativity shows that FTL travel would violate causality, allowing effects to precede causes and creating temporal paradoxes. Proposed mechanisms like wormholes or warp drives require exotic matter with negative energy density that probably doesn't exist in macroscopic quantities. The Alcubierre warp drive requires negative energy equal to about -1 solar mass. Where such energy would come from is unknown and likely impossible. The absence of any observed violations of light speed limit despite billions of years of cosmic history during which advanced civilizations might have developed FTL technology suggests strongly that FTL is impossible. If FTL were possible, we might expect to see evidence of its use by advanced aliens. The fact that we see no such evidence and that all physical phenomena respect light speed limit supports the conclusion that this limit is fundamental and cannot be circumvented by any technology regardless of advancement level. Thermodynamic limits constrain energy use and information processing. The second law of thermodynamics requires that entropy in closed systems increases, which means that all energy use degrades high-quality energy into waste heat. Perfect efficiency is impossible, and practical efficiencies are far from theoretical limits. This means civilizations cannot use energy indefinitely because useful energy sources are finite and are degraded into useless waste heat over cosmological timescales. As stars exhaust their fuel, the universe runs down toward heat death where no useful energy remains. The Landauer limit sets minimum energy cost for information processing at KT line 2 per bit erased, where K is Boltzmann's constant and T is temperature. At room temperature, this is about 3 times 10, negative 21 joules per bit. Modern computers dissipate far more than this minimum, but even computers approaching Landauer limit have finite efficiency. A civilization building optimally efficient computers still faces energy costs that limit total computational capacity. Furthermore, cooling computers to lower temperature to reduce Landauer limit requires energy expenditure that offsets gains. Bremerman's limit sets maximum rate of computation at about 1.36 times 10, 50 operations per second per kilogram of matter based on quantum mechanical uncertainty relations. This is the absolute maximum computational speed, regardless of technology or computer architecture. While enormously faster than current computers, it's still finite, meaning there are limits to how fast any civilization can process information regardless of advancement. Civilizations cannot achieve infinite computational capacity or infinite intelligence. There are fundamental physical limits on information processing. The impossibility of perpetual motion machines means civilizations cannot create unlimited energy from nothing. They must extract energy from existing sources like stars or nuclear reactions or gravitational fields or vacuum energy, but all such sources are finite or have limited extraction rates. The total mass energy available to a civilization is limited by its light cone, which is the region of space-time from which information can reach them given light speed limit. For an old civilization, this might include multiple galaxies, but is still finite and much smaller than the entire observable universe. Proposals for extracting energy from black holes through Penrose process or Hawking radiation face practical difficulties. The Penrose process can extract rotational energy from rotating black holes with theoretical efficiency up to 29%, but requires dropping matter into the ergosphere, which is challenging. Furthermore, only rotating black holes have extractable rotational energy, and once the rotation is extracted, the process stops. Hawking radiation allows extraction of black hole mass energy over extremely long timescales, but the power output is inversely proportional to black hole mass, making it practical only for very small black holes which don't naturally exist. The quantum limits on measurement and control create fundamental uncertainties that cannot be eliminated through better technology. Heisenberg uncertainty principle states that deltax deltap is greater than or equal to 2, where deltax is position uncertainty, deltap is momentum uncertainty, and is reduced Planck constant. This means we cannot simultaneously know position and momentum with arbitrary precision. Similar uncertainty relations apply to energy and time. These uncertainties limit the precision with which any civilization can measure and control physical systems, regardless of technological sophistication. So, examining fundamental physical limits reveals that many capabilities often attributed to advanced civilizations are likely impossible. Faster-than-light travel violates causality and requires impossible exotic matter. Energy use is constrained by thermodynamics and available resources. Computation is limited by Landauer limit and Bremerman's limit. Extraction of energy has fundamental efficiency limits. Quantum uncertainties limit measurement and control. These limits apply universally to all civilizations regardless of advancement. There's no path to arbitrarily advance technology because physics imposes ceilings on capabilities that cannot be exceeded. Now let me examine the timeline and probability calculations that show why the accumulation of barriers makes advanced civilizations extremely unlikely, because understanding the quantitative aspects clarifies why extinction is almost inevitable. Consider a hypothetical intelligent species that has evolved on a habitable planet and achieved basic intelligence comparable to early humans. This species now faces the progression from stone tools to advanced galactic civilization. What are the probabilities it succeeds? The progression requires navigating multiple stages, each lasting thousands to millions of years, and each having extinction probabilities. Let's outline the major stages. Development of agriculture and settled civilization, requiring roughly 5,000 to 10,000 years with extinction probability, perhaps 10% from environmental collapse or resource depletion or social conflict. Development of industrial civilization, requiring roughly 200 to 500 years from start of scientific revolution with extinction. Probability perhaps 20% from resource depletion or environmental damage or social upheaval accompanying industrialization. Development of nuclear age and space age requiring roughly 100 years with extinction probability perhaps 30% from nuclear war or environmental catastrophe or technological disasters. These probabilities are speculative but reasonable given human near misses with nuclear war and ongoing environmental crises. At this stage, the species has achieved our current approximate level, but is not yet advanced in the sense of being detectable at interstellar distances or immune to planetary catastrophes. Avoiding self-destruction through technological adolescence lasting perhaps 1,000 to 10,000 years, during which the species has civilization-destroying weapons and environmental impacts, but hasn't yet developed robust defenses or achieved sustainability or spread to multiple planets. Extinction probability during this period might be 50 to 70% based on the multiple threats, including nuclear war, engineered pandemics, AI risks, environmental collapse, and resource depletion that accumulate over millennia. This is the most dangerous phase because technology creates threats faster than defensive capabilities. Achieving interplanetary presence in home star system lasting perhaps 100 to 1,000 years with extinction probability, perhaps 10% from accidents or social collapse or loss of capability, spreading to nearby star systems requiring perhaps 10,000 to 100,000 years at realistic spacecraft velocities with extinction probability, perhaps 20% from cosmic catastrophes or social fragmentation or technological failures during the extended periods required for interstellar travel, establishing multi-star civilizations spanning 10 to 100 star systems lasting perhaps 100,000 to 1 million years with extinction probability, perhaps 30% from supernovae, sterilizing significant fractions of colonies, or from social fragmentation causing independent evolution and loss of coherence, or from resource constraints limiting expansion, achieving advanced galactic scale presence spanning thousands of star systems lasting perhaps 1 million to 10 million years with extinction probability from GRBs or other cosmic catastrophes or from stagnation and decline, perhaps 50%. If we multiply the survival probabilities from each stage, 0.9 times 0.8 times 0.7 times 0.3 to 0.5 times 0.9 times 0.7 times 0.5 is approximately equal to 0.06 to 0.1, or roughly 6 to 10%. This suggests that of intelligent species attempting the progression from basic intelligence to advanced galactic civilization, only about 6 to 10% succeed. If the extinction probabilities are higher at each stage, the overall survival probability drops proportionally with extinction. Probability of 50% at each of 8 stages. The survival probability is 0.58, is approximately equal to 0.4%. These calculations are highly uncertain because we don't know the true extinction probabilities at each stage, but the key insight is that multiple barriers with individually moderate extinction probabilities combine to create very low overall survival probability, even if we're optimistic about each barrier individually, assuming 70 to 80% survival probability per stage. The product of 8 to 10 such probabilities is only 5 to 17%. More realistic, pessimistic estimates with 50% survival per stage give overall probabilities under 1%. Furthermore, the timescales involved are millions of years during which cosmic catastrophes like supernovae become increasingly probable. If the probability of nearby supernova sterilizing a civilization during any million-year period is 3%, and the progression to advanced civilization requires 5 million years, the probability of avoiding supernova throughout is 0.97. 5 is approximately equal to 0.86, or 86%. This must be multiplied by the survival probabilities from internal barriers, further reducing overall probability. The calculation also assumes that all stages must be completed successfully. Failure at any stage causes extinction, preventing progression to subsequent stages. This creates a series bottleneck where survival requires succeeding at every stage. In contrast, reproduction only requires succeeding once. The asymmetry between the many ways to fail and the single path to success favors extinction over survival. Now we can estimate how many advanced civilizations exist in the galaxy at present. The Milky Way contains roughly 200 to 400 billion stars and perhaps 20 to 80 billion Earth-like planets in habitable zones. If the probability of life emerging on suitable planets is 1%, and the probability of life developing intelligence is 1%, and the probability of intelligent species achieving advanced civilization is 1%, as calculated above, then the expected number of advanced civilizations is 40 billion planets times 0.01 times 0.01 times 0.01 equals 40,000 civilizations having achieved advanced status at some point in galactic history. But most of these civilizations no longer exist if the average lifetime of advanced civilizations is 10 million years due to eventual extinction from cosmic catastrophes or internal collapse or stagnation, and the age of the galaxy is 13 billion years, then at any given moment, the fraction of civilizations that currently exist is 10 million, 13 billion is approximately equal to 0. 0.0077, or about 0.077%. Applying this to the 40,000 total gives about 31 civilizations currently existing. If lifetimes are shorter, at 1 million years, the number drops to about 3 civilizations currently existing. These numbers suggest advanced civilizations are extraordinarily rare at any given time, despite possibly being common over galactic history. The civilizations that do exist are scattered across the galaxy, separated by tens of thousands of light years on average, making detection and communication extremely unlikely. Furthermore, the calculations above are optimistic in assuming relatively high probabilities for life and intelligence emergence. More pessimistic, but perhaps realistic estimates would reduce the numbers by orders of magnitude, potentially to 0 or near 0 advanced civilizations currently existing. So, examining the quantitative probabilities and timescales shows why advanced civilizations are extremely unlikely. Multiple extinction barriers, each with moderate probability compound to create very low overall survival probability. The long timescales required for progression increase exposure to cosmic catastrophes. The result is that most intelligent species go extinct before achieving advanced status, and most advanced civilizations that do briefly exist go extinct within millions of years. At any given moment, the number of advanced civilizations in the galaxy might be 0 to a few dozen at most, explaining why we see no evidence of them. Now, let me examine the implications of advanced aliens not existing for humanity's cosmic future and for how we should think about our place in the universe. Because if we're among the rare, if not unique, examples of technological civilization, this changes how we should value our existence and what we should prioritize. The conventional narrative often assumes that if aliens exist, they're probably more advanced than us because humanity has been technological for only about 200 years, while the universe has existed for 13.8 billion years. If civilizations develop randomly over cosmic history, most should be either far behind us or far ahead. And since civilizations far behind us wouldn't be technologically detectable, while those far ahead would be any aliens we might detect would likely be advanced, this creates expectation that first contact would be with superior beings. But if the barriers to achieving advanced status are as severe as I've argued, then most intelligent species never reach our level, let alone surpass it by orders of magnitude. The filters I've described operate most strongly during the technological adolescence phase, from the development of civilization-destroying weapons through the achievement of sustainable multi-planet or multi-star presence. This is exactly the phase humanity is currently in, having developed nuclear weapons and industrial technology, but not yet achieved sustainability or significant space presence. We're navigating the most dangerous filter period where extinction probability is highest. If most species go extinct during technological adolescence, then the distribution of civilizational advancement is heavily weighted toward the low end. Most intelligent species that survive at all remain at pre-industrial levels, having never developed technology or having developed basic technology but not progressed further. A smaller number reach industrial age but then self-destruct or stagnate. An even smaller number reach our current level, and vanishingly few progress to truly advanced status. This pyramid structure means that civilizations at our level are actually near the upper end of the distribution, not the lower end. The possibility that humanity is among the most advanced civilizations currently existing in the galaxy is initially surprising, but follows naturally from the barrier analysis. If we've navigated challenges that most species fail at, including developing complex multicellular life and intelligence and technology and not yet self-destructing, we're already survivors of multiple filters. The fact that we exist at all means we're exceptional in having survived barriers that eliminate most potential civilizations, we might be not just intelligent, but among the most successful intelligent species in our galactic region at this cosmic moment. This realization should inspire both humility and pride. Humility because our existence is precarious accident, dependent on lucky circumstances and continued vigilance against self-destruction. Pride because we've accomplished something extraordinarily difficult by developing technological civilization and persisting this long. We should recognize our achievement while remaining aware of how easily it could be lost. The possibility that we're alone or nearly alone in the galaxy makes our existence more precious, not less, because we might be the only conscious beings capable of understanding the cosmos in this entire galactic region. The ethical implications are profound. If consciousness and intelligence are rare cosmic phenomena that usually go extinct quickly, then preserving conscious life becomes a cosmic imperative. Every extinction of intelligent species is irreplaceable loss of something valuable and rare. Humanity's potential extinction would not just be tragedy for humans, but would be cosmic tragedy, eliminating possibly the only beings in this region of the galaxy capable of creating art and science and meaning. This creates moral urgency to avoid self-destruction and preserve the conditions for life and consciousness to continue. The responsibility extends to Earth's biosphere more generally. If life is common throughout the galaxy, but intelligence and technology are rare, then Earth is valuable primarily as a biosphere capable of generating intelligence, not as a planet with unique chemistry or geology. Destroying Earth's biosphere through environmental degradation would eliminate not just current species, but the possibility of future intelligence evolving on Earth over the next hundreds of millions of years before the sun's. Evolution makes Earth uninhabitable. This multi-million-year perspective suggests that preserving Earth's habitability has value extending far beyond current or near future generations. The prospect of human extinction raises the question of whether conscious life would ever re-emerge on Earth or elsewhere. If humans go extinct through nuclear war or pandemic or environmental collapse, but Earth remains habitable, would intelligence evolve again from the surviving species? The evolutionary history suggests this is uncertain. Intelligence evolved only once on Earth, despite billions of years and millions of species. Many species have survived for tens or hundreds of millions of years without evolving human-level intelligence, suggesting